In the year 2024, a team of astronomers using the James Webb Space Telescope announced the confirmation of the most distant galaxy ever observed by humanity. It is called JWST Z14-0, and the light we detect from it left that galaxy when the universe was only 290 million years old. The universe is 13.8 billion years old. This means we are seeing a galaxy as it existed when the universe had completed only 2% of its current age. When that light began its journey toward us, the Earth did not exist. The Sun did not exist. The Milky Way was a fraction of its current size. The entire history of our solar system, 4.6 billion years of geology and evolution, and everything that has ever lived on Earth. All of it happened after this light was already 9 billion years into its journey toward us. That light has been traveling toward you for 13.5 billion years. It crossed the vast, expanding space between galaxies, passed through intergalactic voids, was stretched by the expansion of space from its original wavelengths into the infrared, was collected by the 5-meter primary mirror of the James Webb Space Telescope, focused onto a detector chilled to minus 233 degrees Celsius, processed by computers, analyzed by scientists, and eventually became part of the knowledge of a small planet orbiting a middle-aged star in the outer arm of an ordinary spiral galaxy. The light from one of the first galaxies ever to exist, arriving after 5 billion years of travel to tell us what the universe looked like at the very beginning of its story. JWST Z14-0 is surprisingly massive and bright for a galaxy so early in the universe's history. It contains several 100 million solar masses of stars, which is far more than the models of early galaxy formation had predicted for such an early time. It is forming new stars at a rate comparable to much more mature galaxies that existed billions of years later. Its existence, and the existence of other similarly massive early galaxies found by JWST, has prompted a significant revision of our understanding of how quickly galaxies can form and grow. The early universe, it turns out, was far more productive and vigorous than anyone expected. Tonight, we will travel to the distant universe, not with any telescope or spacecraft, but with the accumulated knowledge of thousands of astronomers who have devoted their careers to understanding what lies at the far reaches of space and the beginning of time. We will visit galaxies so remote that the light reaching us now left them before our sun existed. We will explore the young universe in its first billion years, when the first structures were forming from the primordial darkness and the cosmos was finding its shape. And we will rest in the knowledge that this extraordinary journey requires nothing more than closing your eyes. Take a slow, deep breath. Let your body settle completely into wherever you are resting. Let every muscle relax from your face down through your shoulders, your chest, your abdomen, your legs, to the soles of your feet. You are on a small planet in an ordinary galaxy, and the most distant reaches of the cosmos are here tonight, in the quiet, waiting to be explored. To understand distant galaxies, you first need to understand what distance means in cosmology. When astronomers say a galaxy is 13 billion light years away, they mean that the light we currently receive from it left the galaxy 13 billion years ago. But the galaxy is not currently 13 billion light years from us in the way that New York is a certain number of miles from Los Angeles. Because the universe is expanding, the galaxy has been moving away from us for all the time the light was traveling. Today, the proper distance to the most distant galaxies we can observe is about 46 billion light years, even though their light took only 13 or so billion years to reach us. The light was chasing a target that was moving away and caught us only because, even as the target galaxy receded, the intervening space was expanding and the light was always making progress, just slowly. The tool astronomers use to quantify cosmic distances is the redshift. When a galaxy is moving away from us, or more precisely when the space between us and the galaxy is expanding, the wavelengths of the light it emits are stretched. This stretching shifts the light toward longer wavelengths, toward the red end of the spectrum. The more distant the galaxy, the more the space between us and it has expanded during the light's travel time, and the more the light has been redshifted. A redshift of 0 means the galaxy is essentially stationary relative to us. A redshift of 1 means the light has been stretched to twice its original wavelength. Visible light has become infrared. A redshift of 6 means the light has been stretched to 7 times its original wavelength. Ultraviolet light has become near infrared. A redshift of 14, the redshift of Jade's GSZ 14-0, means the light has been stretched to 15 times its original wavelength. These redshifts correspond to lookback times, how far back in the universe's history we are looking. A redshift of 1 corresponds to looking back about 7.7 billion years, when the universe was about 6 billion years old. A redshift of 2 takes us back about 10.3 billion years, to the universe at about 3.5 billion years old. A redshift of 6 takes us back about 12.9 billion years, to the universe at less than 1 billion years old. And a redshift of 14 takes us back 5 billion years, to a universe only 290 million years old. The Hubble Ultra Deep Field, created by combining data taken by the Hubble Space Telescope over 11.3 days of cumulative exposure time of the same tiny patch of sky in the constellation Fornax, remains one of the most scientifically and aesthetically extraordinary images ever created. The patch of sky it covers is tiny, roughly 1/13 the diameter of the full moon, about the size of a grain of sand held at arm's length. It contains approximately 10,000 galaxies. Every single object in the image, with the exception of a handful of foreground stars identifiable by their diffraction spikes, is a galaxy. Some are small, irregular, blue young galaxies at high redshift. Some are large, red elliptical galaxies at lower redshift. Many are in the process of merging with neighbors, their distorted shapes testifying to gravitational interactions that will take billions of years to complete. The Hubble Ultra Deep Field and its successor images the Extreme Deep Field and the Webb Deep Field demonstrate perhaps more powerfully than any other observation the extraordinary population density of the universe. If you point a telescope at any blank patch of sky, anywhere, and observe for long enough, you will find thousands of galaxies. The universe is not mostly empty, it is mostly galaxies, distributed in the vast cosmic web of filaments and clusters and voids, but present everywhere. The Epoch of Reionization is one of the great phase transitions of cosmic history, and understanding it is one of the primary scientific drivers for studying the distant universe. In the first few 100,000 years after the Big Bang, the universe was filled with a dense, hot plasma of protons, electrons, and photons. When the universe cooled enough for electrons to combine with protons to form neutral hydrogen atoms, at a temperature of about 3000 Kelvin and a redshift of about 1100, the cosmos became transparent to light for the first time. This event is called recombination, and it is the source of the cosmic microwave background that we observe today. After recombination, the universe entered a period called the Cosmic Dark Ages. Neutral hydrogen filled all of space, and the only light was the dim, cooling glow of the recombination itself, slowly redshifting from visible light toward the radio spectrum. There were no stars, no galaxies, no sources of light at all. The universe was dark and cold, and mostly uniform, with only the tiny density fluctuations seeded by quantum mechanics in the inflationary epoch to break the monotony. As gravity amplified those tiny density fluctuations over millions of years, regions slightly denser than average grew denser still, pulling in surrounding matter and eventually forming the first dark matter halos, the seeds of the first structures. Within these halos, gas cooled and collapsed to form the first stars, perhaps around 100 to 200 million years after the Big Bang. These first stars, the population 3 stars, were massive and hot and bright, radiating intensely in the ultraviolet. Their ultraviolet photons were energetic enough to ionize the surrounding neutral hydrogen, stripping the electrons from the hydrogen atoms and creating bubbles of ionized gas around each star and each proto-galaxy. As more and more sources of ionizing radiation formed, their ionization bubbles grew and eventually merged, percolating through the intergalactic medium until the entire universe was fully ionized again. This process, the Epoch of Reionization, ended when the universe was between 500 million and 1 billion years old, at redshifts between about 6 and 10. It marks the end of the cosmic dark ages and the beginning of the era when the universe looks roughly as it does today, a universe of transparent intergalactic space populated by galaxies. Understanding the Epoch of Reionization, which sources drove it, how quickly it progressed, and what it was like to live through it on a hypothetical planet in an early galaxy, is one of the central goals of modern observational cosmology. Lyman-break galaxies are a class of distant galaxies identified through a technique that takes advantage of a specific spectral feature. Hydrogen gas absorbs photons with energies above a certain threshold, the Lyman limit, so strongly that essentially no light at these energies can escape from a galaxy. Galaxies appear to suddenly drop to zero flux at this wavelength, a feature called the Lyman-break. As the galaxy's redshift increases, the spectral break moves to longer wavelengths. By looking for galaxies that are bright in some photometric bands, but completely absent in others, corresponding to imaging redward of the Lyman-break and blueward of it, respectively, astronomers can efficiently select galaxies in specific redshift ranges. This technique, pioneered in the 1990s, identified thousands of star-forming galaxies at redshifts of 3 and higher and opened the era of systematic study of the distant universe. Let your breathing be slow and steady. In and out. The light from Lyman-break galaxies that astronomers have studied for decades began its journey before the Earth existed. The photons in those telescope images traveled for billions of years through the expanding universe, were redshifted and stretched, passed through the cosmic web of filaments and voids, and finally arrived at a detector in Earth orbit or on a mountain in Chile or Hawaii. Every image of a distant galaxy is a message from the past, a fossil of light that preserves information about a universe that no longer exists in the form we observe. The distant galaxies we see now are long gone. The light arriving tonight is from a younger universe, and those galaxies have evolved into something very different over the billions of years since the light left them. The history of star formation in the universe follows a specific pattern that cosmologists have painstakingly reconstructed from surveys of galaxies at different redshifts. The cosmic star formation rate, the total rate at which new stars are being formed across all the galaxies in a given volume of the universe, was not constant over time. It was very low in the first few 100 million years, rose rapidly through the first billion years as the first galaxies assembled, reached a peak at a redshift of about 2, corresponding to a time when the universe was about 3 to 4 billion years old, and has been declining ever since. The peak of the cosmic star formation rate, sometimes called cosmic noon, was a time of extraordinary activity in the universe. Galaxies at redshift 2 were forming stars at rates 10 to 100 times higher than the most active star forming galaxies in the local universe. The interstellar medium in these galaxies was dense with gas, fed by streams of cold gas flowing in from the cosmic web along filaments, and that gas was being rapidly converted into stars. The giant molecular clouds in these early galaxies were larger and more massive than the molecular clouds in the Milky Way today, and the stars they produced were born in clusters of thousands of stars rather than the tens to hundreds typical of local star-forming regions. The most extreme examples of star-forming galaxies in the distant universe are the Submillimeter galaxies, discovered in 1997 when the scuba camera on the James Clerk Maxwell telescope began detecting point sources of submillimeter radiation from the distant universe. Submillimeter galaxies are forming stars at rates of hundreds to thousands of solar masses per year, compared to the Sun's galactic neighborhood rate of about 1 to 3 solar masses per year in the entire Milky Way. They are among the most luminous galaxies in the universe, but their light is almost entirely absorbed by the dense dust produced by their intense star formation and re-emitted at far infrared and submillimeter wavelengths. From optical telescopes, many submillimeter galaxies are nearly invisible, but at longer wavelengths, they blaze with extraordinary luminosity. The James Webb Space Telescope has fundamentally transformed our understanding of galaxies in the early universe, and has done so in ways that have surprised and in some cases puzzled cosmologists. In its first year of operation, JWST detected numerous massive, well-formed galaxies at redshifts greater than 10, corresponding to times when the universe was less than 500 million years old. These galaxies are far more massive and contain far more organized structure than the prevailing models of early galaxy formation had predicted. They look, in many respects, more like mature, evolved galaxies than the small, irregular, rapidly star-forming galaxies that theorists expected at these epochs. The existence of these early massive galaxies has prompted several responses from the theoretical community. Some researchers have argued that star formation in the early universe was simply more efficient than assumed, converting a higher fraction of the available gas into stars before feedback from those stars could regulate the process. Others have suggested that the stellar mass estimates from JWST are systematically overestimated due to contributions from emission lines or from assumptions about the stellar populations. And some have argued that the observations require genuinely new physics, modifications to the model of cosmic structure formation that go beyond standard cold dark matter. Whatever the resolution, JWST has clearly established that the early universe was far more dynamic and productive than anticipated. The first billion years of cosmic history, which had been largely inaccessible to pre-JWST telescopes, is now yielding its secrets, and those secrets are both more complex and more interesting than imagined. The most distant quasars known are among the most extreme objects in the observable universe. Quasars are extraordinarily luminous galactic nuclei powered by accretion onto supermassive black holes. As gas falls into the black hole's gravitational field, it forms a hot accretion disk that radiates across the electromagnetic spectrum with a luminosity that can exceed the combined output of all the stars in the host galaxy by factors of hundreds or thousands. The most luminous quasars outshine entire galaxies by factors of 100 to 1000. The quasar J0313-1T6, discovered in 2021, held the record for the most distant known quasar at the time of its discovery, with a redshift of 7.64. Its light left when the universe was only about 670 million years old. This quasar is powered by a black hole with a mass of about 1.6 billion solar masses. The existence of such a massive black hole when the universe was less than 700 million years old is deeply puzzling for the reasons we have discussed in other stories. Standard models of black hole growth cannot produce a billion solar mass black hole in less than a billion years. Subsequent searches have found additional quasars at similarly extreme redshifts, and JWST has identified numerous lower luminosity active galactic nuclei at even higher redshifts, suggesting that the seeding and growth of supermassive black holes in the early universe is more widespread and more efficient than previously understood. The study of these early active nuclei is revealing the relationship between black hole growth and galaxy growth in the universe's first billion years, a period that may hold the key to understanding why today's galaxies almost all harbor supermassive black holes at their centers. The coevolution of black holes and their host galaxies is one of the most important discoveries in extragalactic astronomy in the past 3 decades. In the local universe, the masses of supermassive black holes in the centers of galaxies are tightly correlated with the properties of the host galaxy's central stellar bulge, particularly the velocity dispersion of the bulge stars. More massive bulges harbor more massive black holes in a relationship that spans many orders of magnitude. This correlation implies that the growth of the black hole and the growth of the galaxy are not independent processes. They are regulated by feedback between the two. The The leading model for this feedback involves the energy released by the accreting black hole, in the form of radiation and jets of energetic particles, heating and expelling the gas of the host galaxy and thereby regulating or terminating star formation. When the black hole is accreting rapidly, quasar mode feedback can heat or blow away the gas supply of the entire galaxy, shutting down star formation. The galaxy becomes a red, dead elliptical, no longer forming new stars. The black hole's growth is also curtailed because the gas supply is exhausted. The system reaches an equilibrium where the black hole mass and the bulge mass are related in the observed way. Understanding how this feedback operates in the most distant galaxies, where the relationship is still being established, is one of the key scientific goals of JWST observations of high redshift active galaxies. Gravitational lensing, the bending of light by massive objects, has been an extraordinarily powerful tool for studying distant galaxies. Massive galaxy clusters in the foreground can act as gravitational lenses, bending and magnifying the light of galaxies far behind them. The magnification can be factors of 10 to 100 or more for galaxies lying precisely behind the most dense regions of the cluster. This natural magnification allows astronomers to study galaxies that would otherwise be too faint to observe in detail, revealing structures and star-forming regions within very distant galaxies that would be invisible without the lensing boost. The technique of gravitational lensing has been used to study galaxies at redshifts greater than 10, revealing young star-forming clumps in galaxies that existed when the universe was less than 500 million years old. It has allowed the detection of individual very bright stars in galaxies at redshifts of 6 and beyond, stars that are individually among the most luminous in the universe, and it has provided some of the most dramatic visual evidence for the large amounts of dark matter in galaxy clusters, whose gravitational influence produces the striking arcs and multiple images of background galaxies that are a signature feature of deep cluster images. Gravitational lensing also produces a phenomenon called Einstein rings, in which the background source, the lens, and the observer are nearly perfectly aligned, causing the background source to appear as a ring of light around the lensing object. Einstein rings are among the most beautiful structures in astronomy, and they can be used to measure the mass of the lensing object with high precision. JWST has observed Einstein rings of extraordinary clarity and detail, using them both to study the lens galaxies and to examine the amplified background sources. Let your breathing be very slow now. Let it be deep and quiet and complete. The most distant galaxies in the observable universe are not abstract. They are real places, as real as the earth beneath you, filled with stars and gas and dark matter and the same physics that governs everything in the universe. They are simply far away, and their light is old. What we see when we observe them is not what they are now, but what they were. And what they were is the beginning of everything we see today, the first chapters of a 8 billion year story, whose latest chapter is the quiet room you are resting in tonight. The concept of cosmic downsizing is one of the surprising patterns revealed by systematic surveys of galaxies at different redshifts. It might seem natural to assume that large, massive galaxies formed slowly over long periods, while small galaxies formed quickly. In fact, The observational evidence shows roughly the opposite. The most massive galaxies in the universe, the giant elliptical galaxies at the centers of galaxy clusters, completed most of their star formation very early in the universe's history, at redshifts of 2 to 3 or even higher, and are now largely passive, no longer forming significant numbers of new stars. Their stars are old, red, and metal-rich, consistent with having formed rapidly at early times. Less massive galaxies, including spiral galaxies like the Milky Way, have continued forming stars throughout the universe's history and are still forming stars today. And the least massive dwarf galaxies are in some cases still undergoing their most intense periods of star formation even in the present epoch. This pattern, in which the most massive systems form their stars earliest and most rapidly, while less massive systems form stars more slowly and over longer periods, is called downsizing and represents a challenge for simple models of hierarchical galaxy formation, in which large galaxies build up gradually through the merger of smaller ones. Reconciling the observed rapid formation of massive systems with hierarchical structure formation requires efficient feedback mechanisms that rapidly terminate star formation in massive galaxies and sophisticated models of how gas is supplied to and removed from galaxies across cosmic time. Green P galaxies are a class of compact, intensely star-forming galaxies at relatively modest redshifts, typically around 0.1 to 0.4, discovered by citizen scientists participating in the Galaxy Zoo project in 2007. Their name comes from their appearance as small, round, bright green objects in composite optical images. They are extremely compact for their stellar mass, with sizes of only about 1 to 2 kiloparsecs, comparable to the largest star-forming complexes within the Milky Way. They are forming stars at extraordinary rates relative to their mass, with specific star formation rates tens to hundreds of times higher than typical galaxies at the same epoch. Green P galaxies are thought to be analogs of the star-forming galaxies at high redshift that drove the Epoch of Reionization, their compactness and high star formation rates, combined with their relatively modest redshifts, which make them easier to study in detail, make them valuable laboratories for understanding the physics of early galaxy formation. One particularly important property of green P galaxies is that many of them are found to be leaking Lyman continuum photons, ionizing photons that can escape the galaxy and contribute to reionizing the intergalactic medium. This makes them direct analogs of the sources thought to have driven reionization. The intergalactic medium, the diffuse gas filling the vast spaces between galaxies, is not a static background. Its properties change dramatically with redshift, reflecting the thermal history and ionization state of the universe. Before reionization, the intergalactic medium was predominantly neutral hydrogen, opaque to Lyman series photons. After reionization, it became a warm, ionized plasma, transparent to most radiation. The transition is recorded in the spectra of distant quasars. Light from quasars behind the neutral intergalactic medium of the early universe is absorbed so completely at Lyman-alpha wavelengths that the spectrum shows a complete gap at those wavelengths, called the Gunn-Peterson trough, while light from quasars at lower redshift, where the intergalactic medium is ionized, shows only partial absorption. The Lyman-alpha forest is the collection of absorption lines produced by neutral hydrogen clouds along the line of sight to a distant quasar. Each hydrogen cloud produces an absorption line at the Lyman-alpha wavelength as shifted by the cloud's redshift. And since there are many clouds at many different redshifts between the observer and the quasar spectrum shows a forest of absorption lines. The Lyman-alpha forest is a powerful probe of the large-scale structure of the universe, because the density of the forest reflects the density of neutral hydrogen along the line of sight, which in turn traces the overall matter distribution. Detailed analysis of the Lyman-alpha forest has provided some of the best measurements of the matter-power spectrum and the state of the intergalactic medium at redshifts between 2 and 6. The angular diameter distance is a concept in cosmology that produces one of the most counterintuitive results in the study of distant galaxies. In ordinary Euclidean geometry, more distant objects appear smaller because their angular size on the sky decreases with distance. In cosmology, this is true at first. As redshift increases from 0, galaxies appear smaller. But at redshifts greater than about 1.5, something unexpected happens. The angular diameter distance reaches a maximum and then begins to decrease. Beyond a redshift of about 1.5, more distant galaxies actually appear larger on the sky than equally sized galaxies at smaller redshifts, because space has expanded so much between us and them that the light paths diverge differently. This means that if you could see a galaxy at redshift 10 and one at redshift 2 that had identical physical sizes, the one at redshift 10 would appear larger in angular size on the sky than the one at redshift 2. This is not an illusion, it is a genuine consequence of the geometry of an expanding universe, and it has the practical implication that the earliest galaxies, while they are the most distant, are not necessarily the smallest in apparent size, and can sometimes be resolved in detail by telescopes even without gravitational lensing assistance. The question of what lies beyond the observable universe is one that cosmology can address only partially. The observable universe is bounded by the particle horizon, the distance at which the Hubble flow equals the speed of light, beyond which light has not had time to reach us in the age of the universe. The observable universe is a sphere approximately 93 billion light-years in diameter, centered on Earth, the boundary of which represents the region from which light could, in principle, have reached us since the Big Bang. Beyond the particle horizon, the universe continues, but we have no observational access to it. The simplest assumption is that the universe beyond the horizon is similar to what we observe within it, the same physics, the same types of structures, galaxies and clusters and voids, arranged in the same cosmic web pattern. If the universe is truly infinite, or even very much larger than the observable volume, then there are likely regions beyond the horizon that are identical to our local universe, down to the arrangement of galaxies and the presence of a planet very much like Earth. In an infinite universe with finite physical degrees of freedom per unit volume, every possible configuration of matter must recur at sufficient scales, including a configuration identical to the current state of the observable universe with all its inhabitants. Whether the universe is truly infinite or has a finite volume with some topology is not known. The large-scale geometry of the universe appears to be very close to flat, meaning its total volume is either very large or infinite. Measurements of the cosmic microwave background have constrained the overall curvature to be consistent with flatness to within fractions of a percent. If the universe is exactly flat, it is infinite. If it is very slightly positively curved, it could be a closed, finite universe with a volume much larger than the observable portion. The question of whether the universe is infinite remains one of the great open questions of cosmology, and one that may never be definitively answerable from within the observable region. Let your thoughts drift gently outward now, past this room, past this city, past the atmosphere and the satellites and the moon, out past the sun, out through the spiral arms of the Milky Way, out through the local group, through the Virgo cluster, through the Laniatea supercluster, through the cosmic web of filaments and voids that stretches across hundreds of millions of light years, out to the great walls of galaxies, the Sloan Great Wall and the Hercules Corona Borealis Great Wall, the largest known structures in the universe, out to the edge of the observable cosmos, to the faint red-shifted glow of the Epoch of Reionization, where the universe is being lit up for the first time, out to the cosmic microwave background, the afterglow of the Big Bang, the oldest light we can observe, and beyond that, to whatever lies beyond, unknown and unknowable from here. Before rest comes fully, let the distant universe share a few more of its most beautiful and extraordinary stories. The galaxies at the edge of the observable cosmos have much to tell us about how everything we see around us came to be. The Hubble sequence, the classification of galaxies into spirals, lenticulars, and ellipticals based on their visual morphology, breaks down at high redshift. Looking at the most distant galaxies in deep field images, astronomers find a much more irregular, chaotic morphological distribution than in the local universe. Early galaxies often appear as small, irregular clumps of blue star-forming material without the organized disk or ellipsoidal structure that characterizes most local galaxies. Some appear as elongated chains of bright knots called chain galaxies. Others have a compact bright head and an extended faint tail, earning them the nickname tadpole galaxies. These morphologies reflect the tumultuous conditions of early galaxy formation, when accretion of new gas, mergers with neighboring proto-galaxies, and intense internal star formation were all occurring simultaneously. The transition from the irregular, clumpy morphologies of high redshift galaxies to the ordered spirals and ellipticals of the local universe is one of the major processes of galaxy evolution. As galaxies grew, accumulated gas, and converted that gas into stars, their stellar populations settled into increasingly organized configurations under the influence of gravity. Disk galaxies formed when infalling gas conserved angular momentum and settled into a rotating disk. Elliptical galaxies formed when disk galaxies merged with each other, scrambling the ordered rotation and producing a dispersion supported stellar system. The transformation of the universe's galaxy population from chaotic and irregular to ordered and diverse took billions of years, and the evidence for each stage of this transformation is preserved in the light arriving from different distances. Galaxy protoclusters are among the most spectacular structures in the distant universe. A protocluster is a region of space that will eventually collapse under gravity into a galaxy cluster like the Coma cluster or the Virgo cluster, but which at early times exists as an overdensity of galaxies spread over tens of millions of light years. Because proto-clusters are the densest environments in the early universe, they are the sites of the most intense star formation and black hole accretion at high redshift. Surveys of the high redshift universe have found numerous proto-clusters at redshifts of 2 to 4, some of them containing dozens of intensely star-forming galaxies clustered in a region that will eventually collapse into a single massive cluster. One of the most dramatic examples of a high redshift proto-cluster structure is the so-called spiderweb galaxy system at a redshift of about 2.16, corresponding to a lookback time of about 10.8 billion years. The spiderweb galaxy, formerly known as C 1138-262, is a massive galaxy at the center of a protocluster, surrounded by dozens of smaller satellite galaxies, connected to it by filaments of ionized gas, creating a structure reminiscent of a spiderweb when imaged in detail. The filaments trace the cosmic web on the scale of the protocluster, funneling gas toward the central galaxy and its satellites. The system is one of the most studied examples of a galaxy group in the process of formation and has provided important insights into how the most massive galaxies in the universe assembled their mass at early times. The cosmic web plays a fundamental role in the evolution of distant galaxies. In the standard model of structure formation, dark matter halos form in overdense regions and are connected by filaments of dark matter and gas. Galaxies form within these halos, and the gas flowing along the filaments provides a continuous supply of fresh material for star formation. At high redshift, when the cosmic web is denser and the filaments carry a larger fraction of the total gas budget. This cold stream accretion, as it is called, is thought to be the dominant mechanism by which galaxies acquire their star-forming gas. The gas flows in along the filaments, bypassing the hot atmosphere that would otherwise prevent cooling, and feeds directly into the galaxy's star-forming disk. At later times, as the universe expands and the density of the filaments decreases, and as the massive halos of galaxy clusters develop large hot gas atmospheres that quench cold accretion, the supply of fresh gas to galaxies is gradually shut off. This transition from cold accretion to hot halo suppression is one of the key processes in the decline of the cosmic star formation rate from its peak at cosmic noon to its current low level. The universe is, in a sense, running out of cold gas, and the galaxies are becoming increasingly passive and quiescent as a result. The Cosmos Field, the Cosmic Evolution Survey, is one of the most extensively studied patches of extragalactic sky. Centered near the celestial equator in the constellation Sextans, the Cosmos Field has been observed by virtually every major telescope in existence, including Hubble, Spitzer, Chandra, XME Newton, the Very Large Array, Subaru, Keck, and JWST. The multi-wavelength dataset assembled for the Cosmos Field includes photometric redshifts for millions of galaxies and spectroscopic redshifts for hundreds of thousands, providing a three-dimensional map of galaxy evolution across cosmic time and one of the best-studied regions of the sky. The Cosmos Survey has been central to establishing our understanding of galaxy mass functions, the star formation mass relation, galaxy clustering, and the relationship between active galactic nuclei and their host galaxies across the full range of cosmic history. Galaxy morphological evolution, the systematic change in the shapes and structures of galaxies over cosmic time, is one of the clearest signatures of the long-term transformation of the universe. In the local universe, the galaxy population is divided roughly between the blue cloud, star-forming spiral and irregular galaxies with ongoing star formation, and the red sequence, passive, non-star, forming elliptical and lenticular galaxies. With relatively few galaxies in the transition region called the Green Valley, at higher redshifts, the balance shifts dramatically toward the blue cloud. The red sequence is much less populous, and the galaxies on it are somewhat less massive, consistent with the picture of massive galaxies quenching their star formation first, and then accumulating a growing population of quenched lower mass galaxies over time. One of the most puzzling features of the high redshift galaxy population revealed by deep surveys is the existence of massive, compact, passive galaxies at redshifts of 3 and above, corresponding to times when the universe was only about 2 billion years old. These so-called red and dead galaxies have stellar masses comparable to the largest elliptical galaxies in the local universe, but are much more compact, with sizes only about 1/5 to 1/10 as large as equally massive galaxies today. They stopped forming stars when the universe was very young, for reasons that are not fully understood, and they must have grown in size by a factor of 5 to 10 since then through mechanisms that do not involve significant star formation. The leading explanation for this size growth is minor mergers, the accretion of many small satellite galaxies over billions of years, which adds mass primarily to the outskirts of the galaxy. But the details of this process and the question of what caused these galaxies to quench so rapidly at such early times remain active areas of research. Jellyfish galaxies are a visually striking class of objects found in galaxy clusters, where they provide a direct illustration of the effect of the cluster environment on galaxy evolution. As a galaxy falls toward the center of a galaxy cluster, it moves through the hot, diffuse gas that fills the cluster, called the intracluster medium. The ram pressure of this gas on the galaxy's interstellar medium can be sufficient to strip the gas from the galaxy's disk, particularly in the outer regions where the gravitational restoring force is weaker. The stripped gas forms a trailing wake behind the galaxy, creating the distinctive jellyfish appearance, a relatively intact stellar disk with long, bright tentacles of gas and star formation trailing behind it in the direction opposite to the galaxy's motion. Jellyfish galaxies have been extensively studied in nearby clusters like Virgo and Coma, but they also exist in more distant clusters at redshifts of 0.5 to 1, corresponding to lookback times of 5 to 8 billion years. They provide direct evidence for the ram pressure stripping mechanism that is thought to play an important role in quenching star formation in cluster galaxies, transforming them from blue, star-forming spirals into red, passive S0 or elliptical galaxies over timescales of a few billion years. The tentacles of stripped gas can extend for hundreds of kiloparsecs and are actively forming new stars far from the galaxy's disk, in environments very different from normal star-forming regions. Consider what it means that the light from a jellyfish galaxy 6 billion light-years away is arriving at a telescope right now. That galaxy, in its current form, has been evolving for 6 billion years since the light we observe was emitted. It may have completed its stripping and quenching long ago, transformed into a passive red galaxy within its cluster. Or it may have been further disrupted, its stars eventually scattered into the intra-cluster light of the cluster. We will never know what happened to it after the light we observe was emitted, because any subsequent information from that galaxy traveling at the speed of light will take another 6 billion years to reach us. Looking at the distant universe is, in this sense, profoundly melancholy and profoundly beautiful at the same time. We see these ancient, evolving galaxies. We understand something of what they were going through when the light we see was emitted, and then they recede into an irretrievable future that the speed of light places permanently beyond our knowledge. The universe is full of stories. We can only read up to a certain point, and then the page turns to a chapter that will not arrive for billions of years. Let your breathing be very slow now. In, deeply and gently, filling your lungs completely, and out slowly, letting everything go. The distant galaxies are in their ancient light. The universe is enormous and old and astonishingly productive and creative. And tonight, in this quiet room, on this small planet, you are resting in the accumulated light of all of it. The distant galaxies will still be there when you wake. The James Webb Space Telescope will still be collecting their ancient light, pixel by pixel, building up our understanding of the early universe one photon at a time. The astronomers who analyze that data will still be working on their questions. The universe will still be expanding. The cosmic web will still be evolving in its glacially slow way, and the last light from the Epoch of Reionization will still be arriving at our detectors, carrying information about a time before the sun, before the earth, before any of the history we know. There is still more the distant universe has to offer tonight. The cosmos is extraordinarily generous with its stories. The cosmic infrared background is the total accumulated infrared light from all the galaxies that have ever existed, integrated across all of cosmic history. Just as the cosmic microwave background is the afterglow of the Big Bang itself, the cosmic infrared background is the afterglow of all the star formation that has occurred in galaxies since the universe became transparent. When infrared telescopes measure the total brightness of the infrared sky after subtracting the foreground emission from our own solar system and galaxy, the residual glow is the summed light of trillions of galaxies across billions of years of cosmic history. This accumulated glow carries information about the total energy output of all stellar populations and about the dust that absorbed and re-radiated their light. Resolving the cosmic infrared background into individual galaxy contributions has been a major scientific goal of infrared astronomy, and telescopes including Spitzer, Herschel, and JWST have resolved progressively more of the background into individual sources. Stacking techniques have become essential tools for studying populations of galaxies that are individually too faint to detect, but whose properties can be determined statistically by averaging many images at known positions. if you know where a large number of faint galaxies are. From a photometric redshift catalog, for instance, you can align and average their images to reveal the mean properties of the population. The noise in the stacked image decreases as the square root of the number of images stacked, so stacking thousands of galaxy positions can reveal an average galaxy that is far below the detection threshold of any individual observation. Stacking has been used to measure the average ultraviolet emission, infrared emission, radio emission, and X-ray emission of distant galaxy populations, revealing how the average galaxy at various redshifts converts gas into stars, dust, and energy. Stellar archaeology, the study of the chemical and age distributions of stars in nearby galaxies to infer the histories of those galaxies, is a complement to the direct observation of distant galaxies. The stars in a galaxy carry a record of the galaxy's past star formation history and their ages and chemical compositions. Old metal-poor stars formed early in the galaxy's history from the chemically primitive gas of the early universe. Younger, metal-rich stars formed later from gas enriched by many generations of nucleosynthesis. By measuring the properties of individual stars or star clusters in nearby galaxies, astronomers can reconstruct the star formation history of those galaxies over billions of years without needing to observe the galaxies at high redshift. The Milky Way's stellar archaeological record shows that the galaxy's thick disk, an older, more diffuse stellar component, formed in a burst of star formation about 8 to 10 billion years ago, possibly triggered by the accretion of smaller satellite galaxies. The thin disk, which contains most of the Milky Way's current star formation, formed more gradually over the subsequent billions of years. The galactic bulge contains some of the oldest stars in the Milky Way, with ages approaching 12 to 13 billion years. The globular clusters, which orbit the Milky Way in a spherical halo, are among the oldest stellar populations in the universe, with ages of 10 to 13 billion years, relics of the very early universe preserved in a state close to their original composition. Today's galaxy clusters will be unrecognizable in 5 billion years. As the universe continues to expand, the large-scale structure of the cosmic web will evolve further. The densest regions, the galaxy clusters, will continue to accrete surrounding material and grow larger, while the voids will grow emptier. But the accelerating expansion driven by dark energy will eventually prevent the large-scale structure from continuing to grow on the very largest scales. Superclusters like Laniatea are not gravitationally bound. They will not collapse into a single object, but will be dispersed by the accelerating expansion over cosmic time. Individual galaxy clusters, which are gravitationally bound, will continue to merge and grow, eventually forming larger megaclusters if the dark energy is indeed a cosmological constant. The galaxies within these megaclusters will merge progressively, driven by dynamical friction, until the entire cluster is dominated by a single massive elliptical galaxy at its center, surrounded by a diffuse halo of stars, the brightest cluster galaxy, whose descendants will outlast all other structures in the universe for trillions of years. Let your breathing settle into its slowest, gentlest rhythm now, just enough breath to sustain the quiet of sleep. The universe is conducting its ancient business around you. The James Webb Space Telescope is capturing the light of the most distant galaxies, photon by patient photon. The submillimeter telescopes on the high, cold plateaus of Chile and Hawaii are detecting the far infrared glow of star-forming galaxies at cosmic noon. The radio telescopes are listening to the Lyman-alpha forest and quasar spectra, tracing the filaments of the cosmic web. And billions of light years away, galaxies that existed before the sun was born are contributing their ancient light to the cosmic infrared background that fills all of space. You are part of this. The oxygen in your blood was processed by the stellar nucleosynthesis of stars that burned out billions of years before the solar system formed. Those stars were in galaxies like the ones JWST observes today, blazing brightly at cosmic noon, forming stars at rates that would be extraordinary by today's standards. That oxygen crossed the interstellar medium, was swept up in a molecular cloud, settled into the protoplanetary disk of the young sun, became part of the Earth's ocean and atmosphere, was processed by billions of years of photosynthesis and geology and biology, and eventually became part of you. The ancient galaxies are your ancestors. Their productivity is written in your chemistry. Tonight, rest in the accumulated light of all the galaxies that have ever been. The most distant, the most ancient, the most extreme, and the most ordinary. They are all out there, all contributing to the background glow of the universe, all part of the extraordinary 13.8 billion year story that led through 2 trillion galaxies and hundreds of billions of stars and 4.6 billion years of planetary evolution to this quiet moment. Sleep now. The universe is old and patient and extraordinarily large, and you are exactly where you should be tonight. Good night.